Hello. Hello, Josephine. Hello, Alan. I shouldn't really say hello first, should I? Oh, or good afternoon, Katie. Good good after now and there's Maria. All right. Hello, hello. I'm doing the chat now. Good afternoon, Katie. Good afternoon, Alan. Oh, Alan's a double shot. Hello. Good after sorry. Now it's happening. Okay. Good afternoon, Brandon. Good afternoon, Alexis. Do I actually see? Okay. Good afternoon, Maria. Double shot with good afternoon, Stephanie. More people coming. Good afternoon, Victoria. Good afternoon, Paulina. Oh, and there's Claudia. Good afternoon, Claudia. Good, all right. Good afternoon, Logan. Afternoon, Shy. Good afternoon, Emily. Good afternoon, Jada. All right. I think that's, and who else did I not? And Stephanie. And oh, good afternoon, Shirley. Yes, thank you. All right. And did I say Victoria? I feel like I just recently, oh no, I saw work from Victoria. Okay. Yes, I'm getting to know all of you differently. Some through video, some through avatars, and many through your actual work, which is good. So yes, okay. Hello, everybody. All right, we are. If I didn't say hello to you, maybe it's because you didn't say hello to me. Did I say hello to Brandon? Anyway, hello, everybody. Okay, let's. So here's what we're. I. Okay, I have a plan, but it's also I'm also available for. Which do I want to do first? Let me do my thing first, I think would be best. But if you have questions about that, hopefully you saw the practice exam, which was posted. If you have questions about that today or Wednesday, you can ask them. Let me remind, and oh, quickly, your lab. Sorry, I'm just doing that. You guys have lab. Can you remind me when and with whom you have lab? Oh, hello, Jenna. Okay. Can you remind you have lab hello, excellent. Professor Well, Friday. Okay. Oh, Friday. Interesting. Okay. So what so in lab last Friday, what did Friday 1040, Dr. World? Okay. Thank you. Thank you. So what did you do in lab last Friday? You did the board meeting. And that board meeting was that BMA means board meeting alpha or means board meeting? New. Okay. 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 Thank you. All right. That's helpful and clear. Okay. All right. So just to be clear, so I'm going to go over one problem right now from your homework that is very related to the practice exam. I'll tell you, and very related to your actual exam. Therefore, let me remind you again. Let me remind you two things. What you did in the board meeting is great. I want to hear more about it, and of course, I'll hear more about it from her. But just to be clear, like that's not on your exam. I mean, that's important material, and it certainly is on the final exam and all of that. But it's not on this exam. Just to be clear, what's on this exam is essentially the practice exam. And let me be clear again, which you saw on. Oh, that's good. Right. Thank you, Josephine. Yes. I mean, yeah, that's great. I mean, yes. Good research. I mean, absolutely. I'm glad well, you should see what Josephine just wrote in the chat. Absolutely true. Now, and I'm going to do that to some extent today and Wednesday. Let me say again, if you find old solutions to these, what's on the practice exam, that's great. I mean, I hope you do. Like that's what all these resources are for. I will say anything that I don't anything from your practice exam that I don't directly solve today or Wednesday, and that'll be quite a bit. Anything I don't directly solve right in front of you, you should assume will appear on your actual exam without changing the numbers or anything like that. Like, even if you find it on an old YouTube, all the power to you. And you should, I'm glad Josephine's also sharing that information. Like, anyway, I hope you get, that's like the right, like, class attitude. So anything you find, great. If I directly go over it myself, like today or Wednesday, then that just probably means I would change the numbers or make some detail changes just so that you're not just, copy and pasting. But if I don't go over something, even if you find old versions of it, then I probably won't even make changes to it. So again, so the purpose of that practice exam from last Thursday is not, I don't necessarily give the answers to all of it, but what you've now had is like, you have a week of extra time to look at and prepare yourself and help each other, blah, 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 like that. Okay. So, and I will answer questions about it today or Wednesday, and the more specific, and then the more of them I can answer. But what I'm going to do right now, and good evening. Okay. What I'm going to do right now, well, no, let me think. I'll tell you, I know what I was about to say, but I could shift gears actually. No, yeah. What I'm going to do right now is directly go to homework 7. In homework, I'm going to skip all the way to, in homework 7, the problem. I'll share the, okay, I'll share the screen really quickly. Well, no, it's not worth it. I'm going to go all the way to page. I'm going to go all the way in. It's page. Yeah, it's page 5. So please bear with page 5 in homework 7. No, I guess I will share right now really quick, just so that we're all clear. Page 5, problem 1B, relative velocities in 2D. All right, we're going to share really quick so you can see, so you can take a screenshot or see what I'm talking about or whatever. I'm going to go to this problem right here on your screen right now. Okay, it's from your homework 7, and I'm going to tell you, and I'm going to do it right now. Now I'm skipping on purpose because I'm getting right to the meat. Everything that comes before this in 1D and everything in the homework is like building to this. If you send me a text or an email and say, I want to know the specific answers, I was practicing one of the specific answers to, page 4 or something. If you make it specific and brief, I'll share those with you. But they all build toward this. So I'm going to solve this right now. And I'm also going to tell you, and I'm going to take off the screen in a second. So again, if you don't have this homework, and it doesn't matter whether you've done it or not. I mean, it doesn't matter for the purpose of this class, but this is what I'm going to do. And I want you to know that this is the same problem as in your practice exam, the one toward the end. I don't remember what it's called, but the one that's on a river. You can find it right now. If you, the one that has like I'll find it in a second, but there's a problem in your practice exam that's exactly this, with just different numbers and different words, but it's the same concept. All right, I better hold on, I'll get it so that we all know what I'm talking about. So I'm on purpose solving the homework problem now, so that you still have a chance to practice. I don't know if the screen share just changed. Oh, yeah, I guess it did. Okay. So the problem I'm going to solve is from homework 7, but it is 100% this problem. It even says this problem, free float, on the practice exam is just the Toyota Pontiac problem in disguise. So, and this problem is definitely going to appear on your actual exam. Maybe I change the numbers, maybe I don't, depends like how far we got today. But between these two, you have that much practice to do. I mean, that much practice options. Okay, it's all the same concept. So I'm going to switch back now. I hope I'm not confusing anybody. What I'm going to solve on purpose is a homework problem. If you can do that, then you use that as a model to solve whatever on the practice, and what's on the real thing will be, if not identical, super similar. So I hope that, and then other questions you have on other aspects of the exam, if I don't answer today, I'll answer Wednesday. But I'll tell you that I think this is one of the thickest and probably most central problems on the exam. Like, if you can do this, yeah, I think it's the hardest, most recent material, just about. So I think it's one of the most important things for us to practice right now. Okay, but I do see that Josephine has her hand. I'm sorry. Yes, Josephine.
That was an accident, sorry.
Okay. Oh, okay. No problem. All right, great. No, but you usually have really good questions. So, okay. All right. So let me just ask you, as long as you're clear with what like, you get what I'm about to do. You're good. Or like Josephine or anybody or Maria or Claudia or like, yeah. Okay. Cool. All right. So I'm going to do it. I'm trying to move a little bit quickly so that if there's other questions, I can answer them. So I'm going to switch the screen share. Yeah, I'm going to switch the screen share. Try to switch the screen share. This happens. Okay, here we go. Okay. Now I'm going to put that back on. Okay. All right. Okay. So this is homework. Number 7, page 5. Okay. It's called relative velocities in 2D. Really, what it is, what we're about to do, the whole purpose of this problem is we're going to add velocity vectors in 2D. That's what we're about to do. And I want to make it very clear. Like if you're like you see all physics builds from principles, it builds on itself. So what we're going to do right now, mathematically, computationally, is precisely what we did last Wednesday in class. What we're really going to do is just add 2 vectors together to get a third vector. We're going to place them tip to tail. We're going to divide each vector into components, get the components, add the components together in an XY table, and then put the results of the individual components back together to get one big vector. So it's exactly computationally what we did on Wednesday, only that was on displacement vectors. That's where it's easiest to learn the method. We're now going to apply that method to velocity vectors. So the twist, why this is like an exam problem, the thing that at first seems to make this harder or more of an application is you have to you have to put a little bit more, one has to put a little bit more thought into what these vectors actually mean in the physical world, what it means that we're adding them in, or put another way, how to know which vectors to add together, which vectors of the 3 to add together in order to get the third. So what this is the method of adding vectors combined with the nature of velocity. I mean, concept-wise, this is, as it says on the front board, we're going to take that concept that VAC equals VAB plus VBC. And that's Galileo's principle of relativity, form number 4, right? Case number 3. And we're going to apply it to the method of vector addition. We're going to apply it to that idea that a two-dimensional problem is really 2 one-dimensional problems occurring simultaneously yet independently. So anyway, that's what we're going to do. We're going to apply the concept of velocity to the method of vector addition. All right. So that's what's happening. So let's do it. Right. And the key thing is it's all about how the cars are moving. It's not where they are at any moment. Where they are has nothing to do with what we're drawing or what we're saying. But okay. And someone's here. Sorry. So say this is an exam problem. I mean, it is. Even before it starts asking you questions, we should draw our own diagram of the situation, right? I mean, that's step 1. Diagram and fact pattern. So I've got, so this is very much like the old Pontiac problem, but that they were telling you where things are. Now we're telling you how fast they're going. Okay. So we've got a Pontiac. So first of all, we've got a Pontiac going 30 miles an hour at 30 degrees northeast relative to a Toyota, right? I mean, from the perspective of a Toyota, not from the perspective of Earth, not from the perspective of itself, but from the perspective of a Toyota, which is a perfectly legitimate perspective. So I draw that vector and I'm calling that VPT, Pontiac relative Toyota. Okay, I'm just drawing that. Then I've got a Toyota, which is going southeast, smaller angle but bigger speed. So I'm going to draw like a longer arrow, but a slightly steeper angle if I can. And that's the Toyota relative to a gas station, and that's 60 miles per hour. And it's at 20 degrees southeast. Notice, okay, so I'm just drawing those two vectors. And that second one is VTG. It's the Toyota relative to the gas station. They are being measured from two different perspectives. One person would not, and there is no one person in the world or one perspective in the world that would observe both of these vectors simultaneously, for what it's worth. Okay, and notice also, quick last thing, I'm just drawing my diagram. I'm just setting up the facts that as I was given. But notice each one of them, each one of them is measured, is given its own magnitude and its own displacement. Sorry, I'm doing two things at once. It's given its own magnitude and its own direction. And it has nothing, that magnitude and direction has nothing to do with the other vector. Specifically, what I'm saying is notice that Toyota to gas station vector is 20 degrees southeast. That just means 20 degrees south of some eastern, i.e. horizontal reference axis. It's not in reference to the other vector. Okay, just to make clear. So those are my two facts that I'm given. Is there any other? And then we've got a gas station. Now, I'm going to say this too. You might say, well, what's the gas station doing? I don't know. In a way, that's what we're going to find out in the end. But I would say too, if you ask me, well, wait a minute, how fast is the gas station going? Or if you say to me, so I assume the gas station is at rest or something, I would say, no. The gas station is at rest relative to itself, just like the Pontiac is at rest relative to itself, and the Toyota is at rest relative to itself. Everything is at rest relative to itself. What is the gas station doing relative to the Pontiac? That's what we're ultimately going to find out. What's it doing relative to the Toyota? Well, it's about to ask us that, and we'll know. But is the gas station, what's the gas station objectively, absolutely, in and of itself doing? Meaningless question. Like what I'm ultimately trying to say with all that, and the earlier questions in the other pages try to build you up to understand this. What I'm really trying to say is don't be fooled by the wording of this. There's no other better way to word it. We're not trying to fool you. But don't think for a minute that there's anything special about the gas station. There is nothing special about the gas station or the Pontiac or the Toyota. You might say that the gas station is fixed to the earth. I mean, that might be true, but there's nothing special about the earth is ultimately really the meaning of all of this. Okay, so each of these things has their own velocity. Two of them are given, one is not. We're trying to figure out the third. There's not one of these objects has a perspective that's any more real or correct than any of the others. Like that's the important thing of the whole thing. But okay, so, and we're going to see that right now in effect. So there's my diagram, step one. Okay, then question one. So that's step one. Sorry, so, all right. So question one. What's the velocity of the Toyota relative to the Pontiac? So what we're really asking here is what is VTP? And it's asking velocity, like the vector. So I tend to put arrows over letters when I'm talking about, when it says velocity, it means the vector. It means it's ultimately asking me magnitude and direction. So I connote that with an arrow. I'm also going to say well, all right, so I'm going to say that. It's asking me Toyota relative to Pontiac. Order matters. If it had asked me what's the Pontiac relative to the Toyota, then I would have written VPT. Order matters. Velocity of Toyota relative to Pontiac, and you, again, I know I'm talking a little fast. I don't know if that's good or bad, but you may want to make a note when I say velocity of Toyota relative to Pontiac. In English, what I mean is the velocity of the Toyota as measured by the Pontiac. That means also equivalently the velocity of the Toyota in the frame of reference of the Pontiac, or put one last final way, or well, there's a million ways to put it, the perspective of the Pontiac, etc., the coordinate system of the Pontiac. But maybe the best way to put it, especially for those of you who relate this back to video games or movies or whatever, is that if I ask VTP, I'm saying if the Pontiac regards itself as at rest, if the Pontiac views itself as stationary and looks at the rest of the world moving by it, what does it observe or measure the Toyota to do? That's what we're really asking here. And again, remember, that's not an artificial perspective. That is one of countless equally legitimate perspectives. We want to know here what is the Toyota doing from the perspective of the Pontiac, and here's the answer. Well, first of all, that's the question. If we were doing an exam right now, like, sorry. Going too fast for my own bit, actually. That's the question. What's VTP? Question mark. So that's step 2. What is the question? Okay, so how do I know it? Well, what's the general what's the GDP here? What's the general definition or principle? The general definition of principle is GPR form 4, which is what this whole homework is really about. GPR form number 4, case number 2, the 2 object case. That is to say, what I know is that if I have 2 objects, Pontiac and a Toyota, and I know the velocity of one relative to the other, then the other relative to the one is exactly the opposite. Oh, sorry, that's not what I meant to. This is where the order of the subscripts comes in. If I know Pontiac from the perspective of the Toyota, but someone's asking me the Toyota relative to the Pontiac, then the answer is going to be the opposite in direction, but the same in magnitude as what I was given. That is to say, of course, I've already forgotten what I'm asking. Oh, yeah, okay. So, or if you want to, you can write it either way. I don't know if this is easier to see. VTP is the opposite of VPT as far as vectors are concerned, i.e. So now filling it in for this, and I'm not going to write all the steps every time. I'm just trying to do it once here for the sake of exam practice. I.e. here VPT equaled 30 miles per hour at a direction of 30 degrees northeast. Therefore, and here comes my final answer for this. Therefore, VTP equals also 30 miles an hour, but in the exact opposite direction. The exact opposite of 30 degrees northeast is 30 degrees southwest. Because that's a quick way of saying 2-dimensional problems are really 2 one-dimensional problems at the same time, but independently. That is, the opposite of east is west, and the opposite of north is south. So I'm flipping each positive sign to a negative sign independently, but simultaneously, so to speak. So this is my answer. In English, I'm saying that if the Toyota sees the Pontiac going to the northeast, and really picture it like if you're on the highway, if you see another car going to the northeast away from you, then that car would see you going to the southwest relative to it, right? I mean, I hope that's clear. And you're both right? Like, and if you then ask, yeah, but what are they really doing? I have to say that's not a meaningful question. If you say, what are they really doing? Probably what in your heart of hearts you mean is, what are they doing relative to the Earth? And sure, we could answer that if we know more about the Earth. But then just please remember that whatever they're doing relative to the Earth is maybe it's important on your practical day-to-day concerns. So we use the Earth as a frame of reference a lot, but it's not more objectively true because the Earth is not sitting still at the center of the universe, and you haven't believed that it was since you were in third grade. Anyway, I don't know if that's, but anyway, that's the answer. The answer is 30 degrees. Sorry. This is the whole answer. Sorry. I mean, this is the answer, but we were asked for velocity. So that means a vector. So we have to give a magnitude and a direction. There it is, 30 miles per hour at 30 degrees southwest. Both those pieces of information together constitute the velocity vector. Oh, sorry, I'm looking at, oh, I love how certain people in direct chat like give me constant feedback about whether it's helping them or not, or how. So, okay, so someone in the direct chat is asking, could the PAW also be an explanation in English instead of math? I mean, it can, sure, it sure can. Generally speaking, what's happening in PAW is you're somewhere in a PAW in step 4, you're making you're plugging in the actual numbers of the problem. Like even here I did, like usually when I write the word here, HERE, to start step 4, it's because now I'm about to remind myself or the reader of the specific facts of the problem. So really good question. Like step 3 was saying this concept that the velocity in one direction, it must be the opposite of the velocity in the other direction. But then I go to step 4 and I'm saying, well, here the actual numbers are 30 and 30 degrees northeast. So now I'm flipping those actual numbers here. So, I mean, usually there are specific facts that come up in PAW, but yeah, it might be all English instead of, it might not be equations. That's totally true. Yeah. Good question. All right. I'm going to keep going on, but please keep these questions coming. I'm talking fast. Just so you know, I'm not talking fast to prevent the questions. I'm talking fast, to be honest, so that I can get through the problem and that we still have time for questions. So don't not ask them. So thank you, direct chat person. Okay. So that's that. That's sort of like a warm up, where it's like it's trying to drum in that GP. This is all about really how to use GPR form number 4, which when I first introduced it, a lot of people legitimately asked, yeah, but like, how do we ever use it? Well, here's how. Okay, I'm just going back to my screen. Hold on, bear with me. I'm trying to figure out where the problem is. Okay, there it is. Okay. So now we do. Now, what I'm going to do also to speed this up, I hope it's clear, I'm going to stop labeling all the steps. I hope you get the pattern of how to label the steps. And yes, you need the steps in the exam. That's what they're really for. But here on, and I might get more and more abbreviated in my answers. Okay, question 2. It's asking what's the velocity of the Toyota relative to the Toyota. So what it's asking is, what is VTT? Okay, well, this is, again, I mean, this is GPR form number 4, case 1, the one object case. So I'm right. I guess I still am doing the steps here. I might as well. So that's step 2. This is step 3. And I think this is also where some people get confused. In the GPR, in the principle, as I taught it to you, or as you write it down in your notes, it's the letters A, B, and C. But A, B, and C are meant as arbitrary letters. They're kind of like X and Y and Z in algebra or something. A, B, and C, lowercase, A, B, and C are meant to represent any 3 distinct objects that could ever come up in a problem. So they don't always have to be called A, B, and C. The purpose of these principles is how the velocities of objects relate to one another. So the principle says VAA always equals 0, meaning the velocity of any one given object from its own perspective is always 0. You are never, ever moving from your perspective. Relative to you, you are never moving. Just like relative to Earth, Earth is never moving. And that's like not right. I mean, that's sort of obvious sometimes, but it gets less and less obvious in a way to people as problems get more elaborate. But that's what we're saying. So then we're saying here, okay, the one object in question here is the Toyota, which happens to be labeled with the letter T. So here I'm saying, here A is here here you could say A. By A, we mean T. By the way, even better, what I should have done right from the beginning of this whole problem, I'm switching back now. In my opening diagram, this is actually bad on me. In my opening diagram for this whole problem where I said step 1 DFP, and remember the purpose of diagrams is to provide labels that define all the constants and variables that you're doing in the whole problem. What I really should have added to this diagram, and let me add it now, please, with your forgiveness, what I really should have added in this whole diagram right from the start is I should have said something like, let T stand for Toyota. I mean, it may be as self-evident in my mind as it is in yours, but I should have done it. I should have said from here on, every time we see a T, we mean Toyota. Every time we see a P, we mean the Pontiac. And every time we see a G, we mean the gas station. All right, so those are my three objects now, and any rules that I ever understood about A, B, and C, totally you could substitute these in there for A, B, and C. That's what I'm doing. And I again, it's one of those things, like once you get it, then it seems obvious. But until you get it, it's very confusing, all these letters that are flying around, and people don't, there's nothing special about A, B, and C. It's just the order in which I write them that's special. So anyway, so for the final answer for this one, I hope it's clear. Oops, don't mean to change. Well, the final answer for this one is that the velocity of the Toyota relative to itself, relative to the Toyota, is 0. That's it. It's like a review question where it's to make sure we understand the concept. Okay, this is all using or trying to emphasize or illustrate the relative character of velocities. Okay, so now we get to the real issue of the whole problem, like the real thing. Okay, and all right, it sort of over talks. I mean, the sheet sort of gives, because you've never done this before, it gives you a lot of details as to how to do it. But basically here now in 3, it's asking you to make a diagram, a specific diagram that's going to set up what we're going to try to solve. What it's asking ultimately in 3, it's ultimately asking the velocity of the Pontiac relative to the gas station, right? That's the ultimate question of, which is a big question, of part 3 of this problem, right? And that is not, it's not something that I can't, even if the numbers are nice and straightforward, like 30 and 60 and 20 and 30, I can't do this in my head. It is addition. It is just a addition problem. But we're not literally, we're adding vectors. We're not just adding the numbers 30 and 60 or something like that. Like the answer is not going to be 90 or something like that. I can't do it in my head. It requires picturing and analyzing vectors. So first it asks me to draw a pretty good diagram that will sketch out what's actually going on with this addition. So I'm going to do that. But let me remind you too, this is now the 3-object case, right? We just practiced GPR in the 1-object case, in the 2-object case. This now is a 3-object case. We have a Pontiac, we have a Toyota, we have a gas station. We want to know what the Pontiac is doing relative to the gas station. No one ever told us. And more to the point, no one told us what the gas station is doing relative to the Pontiac. It's not like we can just flip a number the way we did in the last 2 cases. What they told us is what the this is a situation where, well, I'm going to say it now. Like, here's the GDP. The GDP, like GPR, form number 4, case number 3, is in general, right? In general. So I'm writing on step 3 now. I'm not going to write step 3 anymore because I don't want to keep changing inks. But in general, what we know is that VAC, whatever A, B, and C might mean, equals VAB plus VBC. So here, what that means, if you take that same pattern and apply it to these objects, if you want to know what the Pontiac is doing relative to the gas station, that is, for example, what the Pontiac is doing relative to the Toyota plus what the Toyota is, what the Toyota is doing relative to the gas station. That's the pattern, right? This whole thing we're saying is my velocity relative to the subway plus the subway's, I mean, just as an example, my velocity relative to the subway plus the subway's velocity relative to Manhattan adds up to give my velocity relative to Manhattan. That's why I take subways, because the velocity of the subway adds to the velocity of me, as long as they're measured in the appropriate frames of reference. So that's what we're saying here, but it's a lot harder to picture here. I mean, it all goes back to that concept that I just said. And hopefully you can picture that when you stand in a subway, but you get home anyway. That's the idea, that velocities add. But the thing is, when you stand in a subway and you get home, that's easier to picture because, number one, at least one of those numbers involved is a zero. You are going 0 miles an hour relative to the subway. Then the subway is going 80 miles an hour relative to your home. So you're going 80 miles an hour relative to your home. Like, I think most of us can picture that. Number one, there's a zero involved. Number two, it's all in a straight line. It's all one-dimensional, right? So that's the easier to picture version. But what we're trying to say is the concept is still right. And the math is still right. It's a law of physics, even when there's no zeros involved, and even when you're in 2 dimensions, even when it's vectors. So we're saying the velocity of the Pontiac relative to the Toyota plus the velocity of the Toyota relative to the gas station is going to give us the velocity of the Pontiac relative to the gas station. But if we're adding these things up, we're going to add vectors, which are now like diagonal lines, arrows, and we're going to add them up, placing them tip to tail, like add vectors tip to tail, just like we did on Wednesday. So that, okay, so I'm going to do that. That's basically what this whole question is asking me to do. Yeah, velocity, Pontiac relative to Toyota and Toyota. Yeah. Okay. So here we go. So, and notice I think it's even the same numbers. I can't remember, but I think it's even the same numbers as it was Wednesday, but they mean something different now. They're in miles per hour rather than just miles. So we got, I just want to make sure I give myself room. Yeah, it's hard to give myself room. So we've got this 30 VPT equals 30 miles per hour plus 60. This one's going to be longer and something like this, right? And notice my 20 degrees is always, notice that's south of east. So I'm always drawing the angle with reference to some horizontal. This is what you do definitely want to practice. It's not 20. Well, anyway, I've already said it, but so this is my diagram. These are the 2 vectors that are going to be added together. I should make a little more careful. Oops, sorry. These are the 2 vectors being added together. So I place them tip to tail. And so what I'm ultimately going to be solving for, this vector that completes the triangle that goes from the original tail to the final tip, that is V. Well, what is that? That's the sum of those 2 vectors. Like vector-wise, no matter what these vectors represented, that third triangle, that third side would be the sum of those other 2 vector sides. But now we're talking about velocities. So what does it mean? What is it represent? It's the velocity of the Pontiac relative to the gas station. That's what that thing is, that red line. If I do this perfectly to scale, whatever, and then measured everything, the measurement of that red line would be my answer for its speed. And if I had a protractor, the angle that it's making with reference to some horizontal line, this angle here is what I'm looking for, is the direction of that final answer. Okay, so now, okay, so that's the picture that we're asked for in part 3. It's asking us to give us the vector addition diagram. That, again, this diagram would be the computation. Like if I drew all of this with rulers and protractors, then my answer that I'm ultimately looking for would be the measurement of that red line. So this diagram does work. And from it, it's asking. Does it actually ask? I'm just looking if it actually asks us. Yeah, I mean, so like from this, I could estimate, I don't think it's asking me, but an estimated answer from picture is that VPG will be like, it'll be longer than 60, but not as long as 90. I don't know. It looks like it'd be something like, it won't be a lot longer than 60. I don't know, something like 65 miles per hour. We'll find out. And I think the angle is going to be a very, very narrow angle. I mean, something like, just looking at my picture, like, I don't know, 7 degrees. I've no southeast, but it will be, I think, a southeast angle. So that's just an estimate that I can use as a check after I've done all the analysis at the end. Did it ask for anything else? It gave angle references. Okay. So that's the diagram it's asking for. I'm going to do the work and I'm watching the clock. We're going to do the work to get the actual answer. Oh, it doesn't even ask. That's really weird. Oh, it's just asking to do all the drawing. Okay. What's a little bit strange is, could that be? Okay. Funny thing about this homework sheet, just to be clear, is it doesn't ever actually ask you to get the actual answer, but I promise you it does in your practice exam, and it will in your actual exam. So we will here. So let's do that now before I do any more diagrams. Let's analytically get the answer, the actual answer, because that, again, I'm not trying to trick you. That's what you definitely have to do in your practice exam and in your real exam. So let's analytically compute the answer. And what do I mean by the answer? I mean what actually is VPG. Okay, so how do I get that? Like, what is the length and the angle of that red line? How do I get that? I go like this. Use component method. Again, this is what we did last Wednesday. For addition. This works for any kind of vectors at all, for addition of vectors. So what do? Zoom in on each vector individually. So first we're going to zoom in on that Pontiac to Toyota vector. I'm zooming in on it. It's the same. So it's 30 degrees to the northeast, and it's 30 miles an hour. When I zoom in on it, I say, so by zooming in and find its components, find its X and Y components, meaning anything that's pointing northeast is really the sum of something pointing east plus something pointing north. And I always say the horizontal first on purpose. So it's something pointing east plus something pointing north, by which I mean, sorry, I'm just looking at this picture, so I don't know if there's something happening in the chat. Oh, there is something happening in the chat. Hold on a second. Oh, interesting. Okay, good to know. I'm looking at the private chat. Okay, why is T triple equal sign to this question? Why is T triple equal sign to it? Wait, I'm just looking at one of the questions. T triple equal sign to. I'm not. All right, someone's asking. These are all great questions. I mean, I see a lot in the chat. Someone, but I might be misunderstanding this question. Someone, I don't think it's a stupid question, but I might not. But I might be confused by it. Someone's asking, why is T triple equal sign Toyota? If you mean like where I wrote, like here at the beginning, T triple equal sign Toyota, P triple equal. I mean, that is a good question because it's really important to distinguish triple equal signs, double equal signs. And sometimes the line is fuzzy. But what I'm saying is because I'm declaring, I'm defining, I'm saying, I didn't discover that T stands for a Toyota. Like I didn't figure that out, or that didn't happen to turn out that way. I'm literally just deciding. I'm saying when I use T from now on, I mean Toyota. So since it's like a declaration or a definition, I mean, in my mind, it's a definition. I'm just defining that symbol to mean Toyota. It didn't turn out that way. I'm just choosing it that way. I don't know if that, okay. So that's why. If something is a, okay, cool. Okay, awesome. I love the feedback. Okay, great. So I'm, and I hope it's clear to everybody. Please stop me in the thing. Again, if you go back and look at this while you're practicing the practice or practicing the real exam, you'll notice what I just did that actually nowhere in this question. I mean, and for homework, if you never actually got an answer to this, I won't take off any points or anything. The homework apparently, weirdly, didn't literally ask you to solve for this velocity, but I'm doing it now because that's what you need to know for the other documents. Okay, so please, if that's throwing you off, or if you're like, where is he in the homework, I'm getting an answer that the homework apparently didn't explicitly ask for, but it is the point. The point is, okay, so let me know if that's confusing you. And again, if you didn't do it in the homework, don't worry, I won't punish you there. But so we are saying physically, I'm getting the components now, which we always do with any vector problem. Multiple. I'm looking. Sorry, there's something in the chat again. We have multiple questions. Great question. Someone's asking in the chat, like if multiple questions or multiple parts of a big problem all are referring to the same diagram, do you have to keep drawing the diagram again? No, or recopy it? No, you don't. If you keep, and that will happen a lot. Once you've presented a diagram, if you're going to use it a lot, you can keep saying see above or whatever. And eventually, if it's like so many times, you just draw a little arrow. Like, and even same thing with GDPs, general definitions and principles. If you're going to use them over and over again, you don't have to write them over and over again. All of this, these are fine lines and fine judgments, but I'll tell you, I'm glad people are asking them in the chat and so forth, because here's the real deal. There's different judgment calls and people will make different judgment calls, and your style will, different exams are going to look different. But this is actually the whole thing of the exam, is that the more you really know the material, and then you put it all together with your personal judgment calls and your personal styles, like honestly, the more different your exam looks from your friends, like the better someone knows this material, the more their exam is going to really look like their own personal version of all of this. Just like my notes on this, like, and this is not a compliment to me, but my notes don't look like Professor Walters's notes or whomever, right? We could solve the same problem and it just ultimately looks different because we're actually thinking about it. We're not copying it from anywhere, right? You want your exam to be like that. Like by the time, so what I'm saying is, some of these are stylistic questions, like, do I have to recopy the diagram over and over again? Like, short answer, no, you don't. You can keep referring up. But if you're wondering, if you're nervous, you're like, but what's the ultimate standard? Like, how do I know how to make these judgment calls? How do I know how detailed to get with the steps or with the diagrams, et cetera? Here's how you know. Your ultimate standard is you want to give me a document that is as clear and lengthy and thorough and detailed as it could possibly be, such that I don't have to look at any other documents to read, understand, and grade your exam. So therefore, at the beginning of the exam, you want to lay out and the beginning of every problem, you really want to lay things out. You really want to assume I don't have the diagrams in my head anymore or on separate sheets of paper. I don't want to look at separate sheets of paper. You give me everything I need to read your document. But once I'm reading your document and you're on page 4 of your document, of course, then you can assume I still have page 1 of your document. Like, treat it like a book or a presentation or whatever, where as you introduce me to you and to your material, you got to give me everything I need to get involved and to follow and all that. But as you're going along, sure, you can assume that I've been reading what you're telling me and you can just keep referring back to it, right? And I'm being serious. You're practicing for making a journal article, like for publication or whatever. You're trying to give me a self-sufficient document of physics. Well, give me what I need to read it, and then the more it's progressing, the less you need to give me. I hope that's clear. But yeah, for real, it's all about, I don't want to have to look anything else up while I'm reading yours for 1,000 reasons. Okay. Anyway, all right. So we're now going to divide this vector into components. I'll do the math, but then I'll remind you in math to get to the chase, VPTY, so to speak, like the Y component. Maybe I should have done this too. In my original diagram, I probably also should have said something like, in my original diagram, I also probably should have said something like, and I really should have, like anything going up the page means north, and that's positive. Anything going down the page means south, and that's negative for that axis. But then on an independent axis, anything going to the right is east, which we designate positive, and anything going to the left is west, which we designate as negative. And I really should have done that, and you need to do that too, because that's not objectively true. That's a decision I'm making. Like, and you could make a different one, but you got in terms of what you call positive, negative, and all that. But whatever decision you make clear. So here, back to the diagram, VPTY equals, now I'm cutting to the chase here too. This is all using SOHCAHTOA, right? I'm assuming SOHCAHTOA. So I think that side that's opposite the 30-degree angle is hypotenuse times the sine of the angle, right? I mean, I essentially said opposite over hypotenuse equals sine, and then I multiplied both sides by sine, like in my head. Or you could do it on paper, whatever, but we did this on Wednesday. It's always going to be the case that the opposite side is the hypotenuse times the sine, and the adjacent side is the hypotenuse times the cosine. Right? Now, what do those mean? We'll go one step further. If I do them on my calculator, and you, of course, you can use a calculator for this. I recommend for these kind of problems that your calculator be in degree mode. If I were to do this on my calculator, I would get that VPTY is 15 miles per hour. And sorry, I'm running out of room. And VPTX is like 0.87 times 3. So that's going to be like 25, like 20, for, we'll see in a second. Sorry, is point. Oh yeah, 25. Okay, so approximately 25.9 or 26.0. Yeah, I should really say 26. Okay, it's approximately 26.0 miles per hour. And what does that mean physically? What it means physically is that a car that is going, or whatever, yeah, a car that's traveling 30 miles per hour at 30 degrees northeast is equivalent to either of the following. It's equivalent to a car that is going 26 miles per hour to the east, while at the same time it goes 15 miles per hour to the north, right? These are velocities, not distances, not displacements. Every one of these, the length of every one of these arrows does not represent how far anything got. I have no idea how far anything is getting because I don't know anything about time, and I don't need to solve this problem. This is how, all of this is all at an instant. All of this, these are all instantaneous velocities. So it's saying at some given instant, a car that's traveling like this is equivalent to a car traveling like this at a certain rate, while at that moment it's traveling like this at a certain rate. Right, that 26 plus 15 equals 30. Let me say that again. 26 plus 15 equals 30 in the vector sense. If you're taking into account directions, 26 due east plus 15 due north equals 30 at 30 degrees northeast. Again, you should think about that. You should practice that. You should ask me a question about that later if you want. But that's what I'm just looking at the chat. That's what we're saying. Now, I just did that. I just broke up one vector into its two independent but simultaneous dimensions to put that on hold. Like I didn't add any. Well, I'm not adding those to the Toyota or anything yet. I'm just putting those numbers on hold in my mind. I'm also looking at the time. So now I'm going to the other car, to the Toyota. That was all what the Pontiac is doing from the perspective of the Toyota. Now, what is the Toyota doing relative to the gas station, it was doing something like this, right? It was a longer vector, it was the velocity of the right. And notice a subtlety. When I label that hypotenuse, I'm just labeling the length of that hypotenuse. I'm just saying that the speed of this car, this Toyota, relative to the gas station, from the perspective of the gas station, I'm saying the speed of it is 60 miles per hour. The direction of it is that angle, 20 degrees northeast. So the reason there's no arrow over the VTG anymore is because that's just its magnitude information. And the direction information is the 20 degrees. Together, they make the whole vector package that if I were writing on paper, I'd write with an arrow above it. But okay, so I'm zooming in on this. I'm now going to get its two components. Notice southeast really equals some amount east plus some amount south. Like I'm putting arrowheads on those vectors. You need to. If this were on the exam, I can tell you right now, one thing that people do a lot is they draw triangles like this. I think the problem did ask for these triangles. It just didn't ask you to do anything with them. If you draw these, you must draw these triangles, zooming in and figuring things out. They have to have arrowheads. They have to have tips and tails. If they're just raw geometry triangles, people do lose points. Southeast equals east plus south in a vector sense. Does it also equal south plus east? Yes, it does. But if you draw it that way, I'm just advice. If you draw the vertical first, and then from its tip, you draw the horizontal, I'm not saying that's wrong, but it's going to get you all messed up because then the angle you're going to have between the tails is an east-south angle rather than a southeast angle. You should almost practice. This is where practice comes in. I'm writing down the things that are correct, but you don't appreciate them as much until you try and contrast a couple of other options that are less correct. Bottom line of what I'm saying is every time you take a vector and you divide it into two components, the two components have to add together tip to tail, and I recommend that you always draw the horizontal component first. You'll know the horizontal component first. From the tip of the horizontal, draw the tail of the vertical. You'll know you're doing things correctly. I'm going to move on in a second, but you'll know you're doing things correctly if the angles you're looking at, if the angles that you're like referring to, if the angle you care about and is labeled, you might even want to write this down. You'll know it's a good checkpoint if the angle you're looking at is two things. One is measured from the horizontal, not from the vertical. If it's measured from the vertical, then you're going to be talking about east-south rather than southeast, and all your answers are going to be backwards from what would seem to make sense. So number one, your angle has to be measured from the horizontal. And number two, your angle should be, if you're doing it correctly, will always be between two tails, not between a head and a tail, not between two heads, between two tails. That's like a strategy advice. So you see how my angle here is like that. Okay. Okay. Also, I'm just going to make this a little bit smaller just so I can fit my numbers. I'm sorry. I'm not changing it. I'm just making it a little bit. Okay. Okay. All right. So I'm looking in the chat. Okay. There's nothing in the chat. Okay. So what are these two vector components? Well, the horizontal one is VTGX, so to speak. And what that's going to equal is 60 cosine of 20. Cosine because it's the adjacent to the angle. And the other one is VTGY. It'll equal 60 sine of 20. On my calculator, or on a calculator, which I should have gotten out before this class, that would be okay, 50, this one would be 56.4. Okay, so now I have we have 15 minutes. Now I have all the information I need to add things up. All we're trying to do here is add up the vectors, but adding up to two-dimensional vectors really means adding up two sets of one-dimensional quantities independently yet simultaneously. So in other words, okay, so I'm going to make an XY chart. That's what I always do. The XY chart just tries to, I mean, you could present it a different way, but for me, the XY chart is trying to emphasize and clarify that we really have two independent addition problems happening simultaneously. But it's addition. How do we know it's addition, by the way? Like, and I got to warn you too. I mean, I don't even remember in your practice exam or in the real exam, like they could ask ultimately for something that would require subtraction and you do subtract. How would you know? How do you know whether you're adding vectors or subtracting, or how do you know which vectors to add to which? It's all based on VAB plus VBC equals VAC. So if you knew AC and AB and you were being, sorry, if you knew AC and BC and you were asked for AB, you would take that arrangement and you'd subtract something from both sides and you'd realize what you were doing is subtraction. I'll say that again at the end, but how to know? The reason I know this is addition is because of which velocities were given to me and which one I'm being asked for. And I believe I'm being asked for, yeah, I'm being asked for, okay. So VP, so now I'm going to plug in the numbers into this chart. VPTX was 26, approximately 26.0. VPTY was like 15, I believe. But now let's be careful before I move on. Look at this original. Oh, no, that's right. Yeah. VPTX is 26. VPTY is 15. And they both have positive signs on them because the horizontal one's going to the east and the vertical one is going to the north. So they're both positive, right? But now I'm going to add them to the other two numbers, 56.4 and 20, 56.4 and 20.5. But notice, look at my diagram, the 20.5 is going south, not north. So it gets a negative sign. For all I know, there could have been three of these things that get negative signs. I mean, you just look at the diagrams, but that's why the diagrams have to have tips and tails and everything in them. So now I'm literally adding, even though that's a negative sign, I'm adding up because that's what the problem is asking me to do. So I get like 82.2, I believe. Yeah. I'm sorry. I mean, I get 82.4. Hello. Okay. 82.4, right? Yeah. And I get negative 5.5. I don't remember. These might be the same numbers as for Wednesday's problem. I don't even remember. But so what are these? These are miles per hour. This is not how far anything got. This is how fast something is going at an instant. So those are my two independent but simultaneous components. Like this is what this is saying is, in the end of the day, from the perspective of the gas station, what the Pontiac is doing is going 82.4 miles per hour at that instant to the east, while at the same time it's going 5.5 miles per hour to the south. So to get the final answer, and we still have 11 minutes to get the final answer for the final vector, i.e. VPG, we're going to add, literally add, that means tip to tail, the components. We're going to make one big right triangle out of those components. So we're going to go, okay, 82.4, maybe longer. 82.4 is velocity of Pontiac relative to gas station, and the X is 82.4 miles per hour, and it's being added to a comparatively short I should have given myself less. VPGY equals 5.5 to the south, so I draw it down. So the answer I'm looking for, from my original diagram, that long red vector that's pointing to the southeast as we sort of anticipated or sketched, right? This is the answer we're looking for, VPG. So the magnitude of it, VPG, is going to equal the square root of VPGX squared plus VPG. I mean, this is Pythagorean theorem. I'm just square rooting both sides because I think you can handle that. And I don't know why I'm staying in red, but I am. So 82.4 squared plus 5.5 squared. I guess technically it should be 5.50, but what I wouldn't be that. And then square root that. Okay. Yeah, these numbers are very familiar from the last week's problem, and that's fine. So from the perspective of the gas station, the Pontiac is going approximately 82.6 miles per hour. In other words, it's going a little bit faster than that X component because mostly it is going in the X direction, right? Like mostly from the perspective of the gas station, it's largely going east, but it's going a little bit south. Why is that, by the way? I'll finish getting the answer. So the angle, to cut straight to the chase, is the arctan, the inverse tan of the opposite over adjacent, 5.5 over 82.4, right? Which is we want the arctan of that. Right, so like three, yeah, okay. So a really small angle. I didn't really mean to leave all this in red, but here is literally our final answer for all of this. And hopefully it's consistent with the original sketch we made. At the end of the, what this means is, according to the gas station, the Pontiac is going 82.6 miles per hour at a barely southeasterly angle of 3.81 degrees southeast. In other words, it's mostly going east, but it's going a little bit south. Why? Because if you look back at the original numbers, the Pontiac was going north, relative to the Toyota, and the Toyota was going south relative to the gas station, and those numbers were almost identical. So it's like the south and the north aspect of the velocity almost canceled each other out, but not quite. The southern speed was a little bit faster than the northern speed, so a little bit of southern speed was left over, if that makes any sense. Now, this whole answer is from the perspective of the gas station. If the gas station is attached to Earth, which I imagine it probably is, then this whole answer is from the perspective of Earth. But that's not special. I mean, from the sun, if we were to do this, we would get a whole other answer. This is what the gas station sees. If I'm going to just go on, I'm departing from the problem just to help you, well, for a moment, to help you with your exam. Hold on. And I know we have like 5 minutes. Yeah, I will finish the thing. And just in case in your exam it asks something, if someone were to ask, what is the velocity of the gas station? Like, and this is what people always get, or they think, well, wait, what's the gas station doing though? Like, this whole thing is confusing. Didn't he need to tell me? What the gas station is doing, it all depends on what relative to what. If I were to ask, what's the gas station doing relative to the Pontiac? It goes back to the fundamentals. The gas station relative to the Pontiac would be 82.4 miles per hour, or whatever that number was that we just got. 82.6, I'm sorry. 82.6 miles per hour at at 3.81 degrees northwest. It's just doing the opposite to the, if someone were to ask that, the problem didn't, but right. And then finally, what the problem does ask is it asks for these bird's eye diagrams. Right, as for three birds, it asks, okay, so what's happening from each perspective? Like, and it, which is a different way of looking at the same problem. So if we do the gas station bird's eye, someone just came in. I'm looking at the chat. Okay. I'll do one of these. Okay. So the gas station bird's eye, that means there's two. From the gas station, it would see two things. It would see the Pontiac relative to the gas station, right? The Pontiac relative to the gas station, that's what we just solved for. So it would see this long vector at 20 degrees southeast, at 3.81 degrees southeast, V PG would be like 82.6. So that's what the gas station would see the Pontiac doing. But then the other thing is, what would the gas station see the Toyota doing? Well, what would the gas station see the Toyota doing? That was given in the original problem. That would be also southeast, but 20. That would be something like this. And these are miles per hour, always miles per hour, not miles. So a bird's eye view from the gas station perspective would have two vectors, both coming out of, both being tail to tail, because they're both from the same frame of reference. And if we were to do this, I think, if we were to do this from the other two, which we could do on Wednesday, if you want to remind me right when we start, the other two diagrams, I'll just say from Toyota, the other two vectors would be VGT and VPT, right? If you do it from the Toyota's perspective, you look at the two vectors from the Toyota's perspective. And if you look from the Pontiac's perspective, then you'd be looking at you'd be looking at VGP and VTP. And each one of these will have two vectors. And if you stand back and look at all the, how can I put this? Well, I don't want to confuse you. You'll see consistency among all three diagrams. You'll see the same. Look, I'm worried if you ask me first thing on Wednesday, I will draw the other two right when we start on Wednesday so you can see them. But you should practice that before you do. Each one of them will have two vectors coming out of one common tail. And ultimately, each one of them, if you stand back and look at your three diagrams, if you were to complete the triangle for each one in your mind, you'd see that the three triangles are ultimately identical. They're just rotations of one another. And if you think about that, and that's the nature of velocity. What I see you doing is the exact mirror image of what you see me doing. So these triangles will all be the same. These three bird's eye views will all be three of the same triangle, just rotated differently. All right. Now, the good news is we just finished all that. That's a huge that if you could do that, you can do the I already forget what it's called, but you can do the problem on your exam. That's just like it. I will do more of the exam on Wednesday. But the bad news is, of course, I didn't really get to answer any unrelated questions that you might have had. So do bring those Wednesday. Maybe I'll at least on Wednesday, I'll start by asking what questions you have, and then I'll decide which ones, how to spend time on which ones. But no matter what, whether you have questions or not, what I'm going to be doing on Wednesday is going over another exam problem. That I can promise you. But the more questions you come prepared for, the more it might influence like which exam problem I go over or how. All right. So okay. But if that's clear, I hope that was somewhat clear and helpful. If it is, good luck, quark speed to everybody, and I'll see you Wednesday. I'll hang out for a second if there's any other questions, but thank you very much. All right, awesome. Have a great day, and I'll post this, obviously. Okay. Have a great day. Yes. Cool. Thank you for that feedback, Maria, by the way. Oh, thank you. Okay. That means a lot, actually. Okay, cool. Okay. Okay, I'm going to stop the recording. Okay. Okay.